Now let us see how we can use such covariance structures in an actual example. Suppose we are working with our familiar example where we have got a plot as our basic unit and we have variety and different villages in an agricultural study. So we have got different varieties of the same crop and we are trying to see which variety produces more yield or less yield. Now the entire thing has to be carried out over, say, a number of villages. So we have got 3 varieties and 3 villages. So in each village we have got a number of plots under each of the 3 varieties, and then the total amount of yield is measured. Now in such a situation it is quite possible that the way the total yield is measured, that uses certain instruments which are specific to that village. So there is some weighing machine which is used in this village and some other weighing machine that is used in other village. So we expect that village might be having an effect. At the same time, we also expect that the different measurements taken from the same village might be correlated because the same guys took that measurement, so it is possible. Now let us see how we incorporate that. Now in this case the model will take this form yijk equal to blah 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 whatever, and then we will have epsilon ijk. So this I in this case stands for variety, j stands for village, and k stands for the replication factor. So you have got these 3 things. Now we expect that the different entries that share the same j value, they are possibly correlated. Now if I write all this yijk, the entire data vector, or correspondingly all these epsilons, we naturally write it in a way where k runs first test, then j, then this. So the first entry will be 1, 1, 1. The next entry will be 1, 1, 2, then 1, 1, 3. Suppose k goes to up to 5, so 1, 1, 5. After that, this thing will change. 1, 2, 1, 1, 2, 2, and in this way. So if we do it in this way, in that case, all our observations may be colored like this. So the same color in that case I am showing where the same values of j occur. So suppose j takes 3 values. So I have a bunch of things which have, so all these things are under I equal to 1. You see again the same pattern is repeated. This red, green, cyan pattern is repeated. So the first things, so these are all under I1, these are all under I equal to 2, these are all under I equal to 3. Out of these are for j equal to 1, and these are for j equal to 1, these are for j equal to 1. All these green things are for j equal to 2, the cyan things are again for j equal to 2. Now this red block consists of a number of observations depending on k. So all the red things here in the first red block, so these are actually for variety 1, village 1, and k is the only thing that changes. So for all the plots, so all the 5 plots in village 1 where we have shown variety 1. Now when I want to say that all the things that are sharing the j index are going to be correlated, then the covariance matrix that I am going to get will have this particular form. All the 0 entries are shown as white. So white means in this case you have got red in one side and something else, some other color on the other side. So whenever I have red here, so you just imagine that this thing is also shown here because the covariance thing is covariance of epsilon with itself. So these things are all red. So wherever I have red, the red 3 by 3 matrix, it's not really 3 by 3 because these are all blocks. If I assume that each of these things is of length 5, then these are all 5 by 5 blocks. So this entire thing, 15 by 15 submatrix of red, it is scattered all over the place in 9 parts. So you have a 5 by 5 here, a 5 by 5 here, a 5 by 5 here. So all these things are from village 1. So they have a correlation structure. So I mentioned this example so that you understand when I say block diagonal structure, do not think that all the blocks are together. Depending on how you have sprinkled the different yijk's over your y vector, these blocks may be scattered all over the place. They do not really look like a block diagonal matrix. The blocks are scattered all over, but they are actually like that. They are all symmetric around the diagonal. And similarly, all the green blocks, they are also form a 15 by 15 submatrix, but it is scattered all over the place, similarly for the cyan thing. So this is the covariance structure. Now for the red part, you may have, say, compound symmetry, in which case that contributes two covariance parameters, each sigma square and each rho. So it is sigma 1 square and rho 1. Similarly, for the green part, you may have, say, autoregressive structure. So that contributes each sigma square and each rho. So sigma 2 square and rho 2. Similarly, for the third one, you may just assume that these are all uncorrelated and have same variance. So in that case, it will possibly be just sigma 3 square. So your theta vector, the covariance parameter, will become sigma 1 square, sigma 2 square, sigma 3 square, rho 1 and rho 2. It's a 5-dimensional parameter with complicated restrictions such that the entire matrix remains a PD matrix.